This lesson, we'll look at fuel quantity measuring systems. Fuel quantity can be measured by one of two methods. Either the volume of the fuel can be measured, or the mass or weight of the fuel can be measured. Volume measurement can be achieved by having a float in the fuel tank, attached by a suitable mechanism to a variable resistor. The cockpit gauge is normally an ammeter, calibrated in gallons or litres in a circuit with a resistor. As the fuel level decreases, the resistance increases. This leads to a reduction of current in the circuit, so the indication on the ammeter decreases. The gauge is calibrated to show the correct fuel quantity with the aircraft in straight and level flight. This system is normally restricted to light aircraft. It has two major drawbacks. Firstly, it is subject to maneuvering error. That is to say, as the aircraft's attitude changes, the indicated fuel quantity will change. Secondly, this type of system cannot compensate for changes in the specific gravity of the fuel, so, as the fuel gets colder, the indicated quantity will decrease, and vice versa should the fuel temperature increase. On modern gas turbine-engined aircraft, it is important that we measure the fuel on board the aircraft in terms of weight or mass rather than volume. There are a number of reasons for this. Firstly, it is important to know the weight of the fuel in the aircraft for airframe performance reasons. And secondly, the energy in the fuel is measured by weight or mass, not volume. So the pilot needs to know the weight of the fuel that he has available. Measuring the weight or mass of the fuel is done by having variable capacitors in the fuel tanks. The capacitive method works by supplying the two plates of a capacitor with alternating current. The current that flows in the circuit now depends on four factors: the level of the voltage applied, the frequency of the supply, the size of the plates, and the dielectric constant of the material separating the plates. In our circuit, three of these factors are fixed, and the fourth, the dielectric constant, is variable because the dielectric consists of fuel and air. A dielectric consisting of fuel will allow more current to flow in the circuit than a dielectric of air will. The level of current flow will therefore be proportional to the volume of the fuel in the tank. By measuring this current, we can know the volume of the fuel in the tank. If the temperature of the fuel drops, the volume of fuel in the tank will decrease, causing a drop in the current. The opposite will happen if the fuel temperature increases. The dielectric constant of fuel changes when its specific gravity changes. If the specific gravity of the fuel increases, more current will be allowed to flow in the circuit, and similarly, if the specific gravity decreases, the current flow will decrease. When the volume of a fuel reduces because of a reducing temperature, its specific gravity increases, and vice versa when the temperature increases. The system is designed so that these two changes cancel each other out. The capacitor type of system is therefore able to measure the mass rather than the volume of fuel. There is, however, still the problem of attitude error. To compensate for changes in attitude, the capacitive system has a number of capacitor probes in the tank connected in parallel to average the measurement of the fuel in the tank. In this way, as the attitude changes, a fuel level increase is sensed by one capacitor and a decrease is sensed by another. This enables the system to give an accurate indication irrespective of the aircraft attitude. On older aircraft, with analog fuel quantity gauges, if the fuel tank's capacitive gauging system fails, it does so in a manner to draw the attention of the user. A fail-safe circuit is incorporated which drives the gauge pointer slowly towards the empty position in order to prevent the indicator showing that there is more fuel in the tank than there actually is. Some systems also incorporate a test switch, utilizing the fail-safe circuit. When the test switch is operated, the indication moves towards empty, and when the switch is released, the pointer should move back to its original position. On more modern aircraft, the digital gauges are controlled by a fuel quantity indicating system, or FQIS computer. This computer monitors the system for any failures and generates appropriate warnings. In the event that the electrical fuel quantity measuring system fails, or if there is any doubt about the quantity of fuel on board, aircraft are fitted with a simple manual backup system to determine the quantity of fuel on board before flight. One method is to use a dipstick in the top of the tank, but of course this exposes the user to the dangers inherent of walking on high and possibly slippery wing surfaces. Another method is the dripstick. This is a calibrated hollow tube which is withdrawn from the undersurface of the tank through a fuel-proof aperture. When the top of the tube becomes lower than the fuel level, the fuel will drip through the tube, hence the name dripstick. The volume of the fuel in the tank can be established by reference to the calibrations on the tube. The disadvantage of this system is that the user's armpit soon becomes saturated with the fuel dripping from the pipe. A more user-friendly version of this system is the dropstick, or magnetic level indicator. This system uses a rod calibrated to show the level of the fuel in the tank. The rod is fitted within a tube, sealed from the fuel in the tank. Around the tube is a magnet supported on a float. The magnet moves up and down the tube with the fuel. The tip of the rod is also fitted with a magnet. When the rod is lowered through the tube, as the two magnets line up, their fields attract each other, and resistance to further movement will be felt. These systems all establish the volume of fuel in the tank. The weight or mass can be calculated, provided the specific gravity of the fuel is known. Many aircraft have tables for doing this. The fuel system instrumentation on a light aircraft will consist of contents and pressure gauges as shown here. On large aircraft, it is necessary to provide more information than this to the crew. On older aircraft types, the fuel control panel is usually in the form of a mimic diagram with flow bars and lights to indicate flow. More modern systems have electrically presented schematic displays. The diagram here shows a typical Airbus system display. Modern Boeing aircraft have similar displays. The temperature of the fuel in each tank is shown here. This is important information for monitoring the system for fuel icing or fuel waxing. The fuel tanks are shown schematically. with the mass of the fuel in each tank being displayed. The wing tanks are split into inboard and outboard sections. In this instance, the outboard tanks are empty, as is the center tank. These symbols are used to indicate the position of the main tank outboard to inboard transfer valves. In this case, they are open. When closed, they look like this. These symbols are used to depict the fuel booster pumps. The line in the box is vertical when the pump is operating, as seen on the wing tank pump indications, and horizontal when the pump is switched off, as demonstrated by the center tank pump indications. The cross-feed valve indication is in line when the valve is open and cross-line when it is closed. The engine and auxiliary power unit shut-off valve indications operate in a similar manner. The fuel used by each engine since startup is displayed here. And finally, there is a readout of the total fuel on board here. That is the end of the lesson. Remember that light aircraft may have a fuel quantity measuring system consisting of a float attached to a variable resistor. The two problems with this system are that the indicated quantity of fuel will change when the specific gravity of the fuel changes, and the system will give erroneous indications during maneuvers. Most large aircraft use a capacitance type of system, which uses the difference between dielectric qualities of air and fuel to measure the quantity of fuel in the tank. This type of system is unaffected by specific gravity changes, and by using numerous detectors in the tank, it does not suffer from maneuvering error.